The dominant worldview was the geocentric theory, which placed Earth at the absolute center of everything. It took immense intellectual struggle and the work of astronomers like Nicholas Copernicus to transition to the heliocentric theory, correctly placing the Sun at the center of our solar system. Today, science recognizes that nothing is truly static. Even our Sun is in constant motion, orbiting the center of the Milky Way galaxy. To understand how our specific solar neighborhood formed, scientists have proposed several models over the centuries. These include Immanuel Kant's gaseous hypothesis, Laplace's nebular hypothesis, the Chamberlain-Moulton planetesimal hypothesis, and the accretion model by Schmidt and Safronoff. Each of these theories attempts to explain the complex process by which the Sun and its orbiting planets coalesced out of early cosmic material. Zooming out from our solar system, we must ask how the entire universe began. The prevailing cosmological model is the Big Bang theory. It posits that all matter and energy in the universe originated from an extremely hot, dense singular point. Approximately 13.7 billion years ago, this singularity began to expand rapidly, and the universe has been expanding ever since. As the universe expanded, certain regions exhibited slightly higher gravity, seeding the formation of galaxies. The reason for this localized gravity is attributed to dark matter. Dark matter acts as the cosmic glue that holds structures like galaxies together. It is considered a profound mystery because it does not interact with electromagnetic radiation, meaning we cannot see it directly. We only know it exists because of its gravitational effects. While dark matter pulls things together, dark energy does the exact opposite. It is the mysterious force responsible for driving the accelerating expansion of the universe, pushing large-scale structures apart. Like dark matter, dark energy cannot be observed through electromagnetic sensors. Together, these two invisible phenomena make up the overwhelming majority of the universe, with ordinary visible matter comprising only a tiny fraction. Within the high-gravity regions created by dark matter, enormous quantities of hydrogen gas and cosmic dust accumulated to form galaxies. Inside these galaxies, the process repeats on a smaller scale. Localized concentrations of hydrogen and dust gather to form a nebula, which is simply a hot ball of gas and dust. When a nebula is specifically involved in the creation of stars, it is referred to as a stellar nebula. The life cycle of a star begins in a stellar nebula. As gravity pulls hydrogen atoms toward a central point, the material collapses inward, forming a dense, contracting object called a protostar. As contraction continues, the pressure and temperature at the core become so extreme that hydrogen atoms are forced to fuse together, creating helium. The moment this nuclear fusion begins, the protostar officially becomes a main sequence star. Hydrogen, the simplest and abundant element in the universe, serves as the primary fuel for main sequence stars. Our Sun is currently in this phase, with enough hydrogen to keep shining for another 3 to 4 billion years. However, hydrogen is not infinite. When a star exhausts its core fuel, its life cycle reaches a critical fork, and its ultimate fate is determined entirely by its mass, specifically whether it is less than or greater than 8 times the mass of our Sun. For a star with a mass less than 8 times of the Sun, exhausting its hydrogen causes a drop in outward radiation pressure. Gravity compresses the core, but the outer layers expand enormously, cooling and shifting in color from blue-white to red. This is the red giant phase. Eventually, these expanded outer layers gently separate from the core, drifting away to form a glowing shell of gas known as a planetary nebula. Once the planetary nebula dissipates, all that remains is the exposed, extremely hot core of the original star, known as a white dwarf. It is called white because it emits all wavelengths of visible light as it slowly radiates its residual energy into space. Theoretically, after an unfathomable amount of time, a white dwarf will cool completely and emit no light at all, becoming a black dwarf. However, the universe is likely not old enough for any black dwarfs to exist yet. If the original star is massive, exceeding 8 times the mass of the Sun, its expansion is far more dramatic, becoming a colossal red supergiant. Unlike smaller stars that gently shed their layers, the immense gravity of a supergiant holds on to its outer material until a catastrophic collapse triggers a supernova. This is an extraordinarily powerful explosion that violently blasts the outer layers into space, briefly outshining entire galaxies. After the violent supernova explosion, only the dense core remains. The fate of this remnant depends on the original star's mass. If the star was between 8 and roughly 25 times the mass of the Sun, The core collapses into an incredibly dense neutron star. If the original star was even more massive, exceeding 25 solar masses, the gravitational collapse is absolute, resulting in a black hole. To predict these stellar outcomes with precision, astrophysicists use the Chandrasekhar limit, named after the Indian scientist Subramanian Chandrasekhar. It is crucial to note that this limit applies exclusively to the mass of the leftover remnant core, not the original star. If the remnant core is less than 1.44 times the mass of the Sun, it becomes a white dwarf. If it is between 1.44 and 3, it becomes a neutron star. If it exceeds 3 solar masses, it collapses into a black hole. Stars are also classified by their age into 3 populations, numbered counterintuitively from oldest to newest. Population 3 stars are the oldest, forming shortly after the Big Bang, over 10 billion years ago. Because the early universe contained almost exclusively hydrogen, these stars were extremely metal-poor. Without heavier elements to regulate their nuclear reactions, they burned through their fuel furiously and died very quickly, meaning they remain purely theoretical and have never been directly observed. As population 3 stars died in supernovae, they seeded the universe with the first heavy elements, or metals. This led to population 2 stars, which are intermediate in age, metal-poor, and boast the longest lifespans. Eventually, further enrichment of the cosmic medium gave rise to population 1 stars. These are the newest, metal-rich stars, typically found in the spiral arms of galaxies. Our own Sun is a population 1 star, formed roughly 4.6 billion years ago. Let us look closer at neutron stars. The gravity in these remnants is so intense that protons and electrons are crushed together to form neutrons. They are almost entirely composed of neutrons and are unfathomably dense. A single teaspoon of neutron star material would weigh as much as the entire Earth. A rapidly spinning neutron star is called a pulsar. For examination purposes, remember that while a pulsar is a star, similar-sounding terms like quasars and blazars refer to active galactic nuclei, not individual stars. The most extreme stellar remnant is the black hole. To understand them, we must understand escape velocity, the minimum speed required to break free from an object's gravitational pull. Earth's escape velocity is about 11.2 kilometers per second. The fastest thing in the universe is light, traveling at 300,000 kilometers per second. A black hole's gravity is so immense that its escape velocity exceeds the speed of light. Because nothing can travel faster than light, absolutely nothing can escape a black hole, rendering it completely dark. While the black hole itself is invisible, it has a distinct structure. The boundary separating the black hole from the observable universe is the event horizon, the absolute point of no return. Surrounding this is the accretion disk. As dust, gas, and planetary debris are pulled toward the black hole, they spiral inward, colliding and generating immense heat and light. It is this intensely bright accretion disk that allows scientists to indirectly detect and photograph black holes. If an object approaches a black hole, it experiences an extreme gravitational gradient. The pull on the side closest to the black hole is vastly stronger than on the far side, stretching the object into a long, thin strand in a process aptly named spaghettification. Furthermore, physicist Stephen Hawking theorized that black holes are not entirely silent. They theoretically emit a faint energy known as Hawking radiation, which would cause them to slowly evaporate over billions of years, though this remains unobserved. It is critical to make a clear distinction here. Black holes are not dark matter. A black hole is simply a dead star, a remnant composed of ordinary matter that has been compressed to an extraordinary density. Dark matter, on the other hand, is an entirely different and unknown physical phenomenon that makes up a massive invisible component of the universe. Both are dark, but they are fundamentally different entities. Any object with mass warps the fabric of spacetime, creating ripples known as gravitational waves. While everyday objects create undetectable waves, massive cosmic events, like 2 black holes merging, create waves powerful enough to be measured. The LIGO Observatory made history by detecting these waves, earning a Nobel Prize. This breakthrough is revolutionary because it allows us to listen to the universe without relying on electromagnetic radiation, potentially opening a new window to study dark matter. Turning our attention to our own star, the Sun is organized into 6 distinct layers, 3 internal and 3 atmospheric. The innermost layer is the core, where extreme temperatures drive the nuclear fusion of hydrogen into helium. Surrounding the core is the radiative zone, where energy slowly travels outward purely as electromagnetic radiation. Finally, the outer internal layer is the convective zone, where churning currents of hot plasma physically transport heat up toward the surface. Above the internal layers lies the sun's atmosphere. The innermost atmospheric layer is the photosphere, which is the visible surface we see from Earth. Above that is the chromosphere, a reddish layer visible during solar eclipses. The outermost layer is the corona, extending millions of kilometers into space. Mysteriously, the corona is millions of degrees hotter than the photosphere closer to the core, an unsolved puzzle known as the coronal heating problem, currently being studied by the Parker Solar Probe.
Because the corona is so unimaginably hot, the material within it does not exist as a standard gas, but as plasma, the fourth state of matter. When a gas is heated to extreme temperatures, its atoms dissociate. Electrons are stripped away from their nuclei, creating a highly energetic soup of free negatively charged electrons and positively charged ions. Understanding this superheated plasma is essential for understanding solar weather.
This coronal plasma is constantly interacting with space. Solar wind is the steady, continuous stream of charged particles released from the corona in all directions, much like a gentle, constantly running tap. However, occasionally, the outward expansive forces of the plasma overcome the sun's gravity, resulting in a coronal mass ejection, or CME. A CME is a sudden, explosive event where massive quantities of physical plasma are violently ejected into the solar system. Often confused with CMEs, solar flares are fundamentally different. A solar flare is a sudden release of pure energy, not physical mass. The sun's powerful magnetic field lines can become highly twisted, storing immense potential energy, like a stretched rubber band. When these lines finally snap back to their original configuration, they release a massive burst of energy, a solar flare. While flares and CMEs are distinct, the energy from a flare can excite coronal plasma enough to trigger a CME. When a coronal mass ejection happens to be aimed directly at Earth, the incoming wave of charged plasma collides with our planet's magnetic field, creating a geomagnetic storm. Because moving charged particles have magnetic properties, they interact intensely with Earth's magnetosphere. While these storms do not cause physical weather events like rain or earthquakes, they can severely damage modern technological infrastructure, disrupting communication networks, frying electricity grids, and endangering satellites and astronauts. One of the most beautiful consequences of solar activity is the aurora, or polar lights. These dancing curtains of light appear in the upper latitudes. In the northern hemisphere, they are known as the aurora borealis, and in the southern hemisphere, the aurora australis. Despite the different names, the physical phenomenon is exactly the same, driven by the interaction between solar particles and our atmosphere. To understand why auroras occur at the poles, we must distinguish between geographic and magnetic poles. The geographic poles are the fixed ends of Earth's rotational axis. The magnetic poles, however, are generated by the churning liquid iron in Earth's outer core. Because this liquid is always moving, the magnetic poles constantly drift and even undergo complete reversals over hundreds of thousands of years. Compasses point to the magnetic pole, not the geographic one. The formation of an aurora is a precise sequence of events. Incoming charged particles from the solar wind or a CME are attracted to Earth's magnetic poles. As they are funneled down into the upper atmosphere, they collide at high speeds with nitrogen and oxygen molecules. These collisions transfer kinetic energy, exciting the atmospheric molecules. To return to their normal state, the molecules release this excess energy as photons, creating the brilliant green, red, and blue lights we see from the surface. Not all incoming solar particles reach the atmosphere. Many are captured by Earth's magnetic field in two donut-shaped regions known as the Van Allen radiation belts. These belts act as a protective jail. The outer belt stops the lighter, negatively charged electrons further away from the planet, while the heavier, positively charged protons penetrate closer before being trapped in the inner belt. They only allow particles to slip through at the poles, which is why auroras are localized there. Solar activity is not constant. It fluctuates over an 11-year period known as the solar cycle. This cycle is tracked by observing sunspots, dark, cooler regions on the photosphere. When sunspot numbers are high, the sun is in a solar maximum, producing more flares, CMEs, and overall energy. When sunspots are scarce, it is a solar minimum. Multiple 11-year cycles also combine to form a larger 400-year cycle, which can influence long-term climate patterns on Earth. Earth's magnetic field is fundamentally responsible for making our planet habitable. By deflecting the relentless solar wind and trapping radiation in the Van Allen belts, it prevents our atmosphere from being stripped away and protects biological life from severe cellular damage. This magnetic shield not only preserves our air, but also provides the foundation for compass navigation and the extraordinary migratory journeys of countless animal species. As we continue our exploration of Earth's fundamental characteristics, we will next examine the precise conditions that allow life to thrive within our solar system. Moving right into the theories of how our solar system formed, let's look at Immanuel Kant. A renowned polymath, Kant proposed the gaseous hypothesis. He suggested that space was initially filled with solid, pre-existing primordial matter. Due to gravity, these solid particles began colliding. As basic physics tells us, collisions generate heat. This progressive rise in temperature melted the solid matter into liquid, and eventually into a massive, glowing gas cloud, which Kant called a nebula. Kant argued that these collisions also caused the nebula to start rotating. Imagine putting powder on a spinning basketball. The rotation flings the powder outward. Similarly, as the nebula spun, successive rings of material separated from its outer edges. The central mass that was left behind became the sun. Meanwhile, the material in those separated rings cooled down and coagulated, or gathered together, to form the planets. This same process repeated on a smaller scale around the planets to form their moons. While groundbreaking, Kant's theory had two major flaws. First, he assumed the primordial matter was just already there, completely ignoring where it came from. Second, and more importantly, the laws of physics dictate that simple, linear collisions do not generate continuous, sustained rotational force. So the spinning motion of the nebula, a crucial step in his story, was physically unexplained. To fix these issues, Pierre-Simon Laplace introduced the nebular hypothesis. Laplace was pragmatic. He skipped the problematic early steps by simply assuming a hot, rotating nebula already existed. He then applied a basic rule you learn in elementary school. Things expand when heated and contract when cooled. Since the hot nebula was in the cold environment of space, it lost heat, cooled down, and began to contract. As Laplace's nebula contracted, its rotational speed increased, much like a spinning ice skater pulling their arms in. This is the conservation of angular momentum. As it spun faster, the centrifugal force, the force pushing outward, became so strong that the outer layers separated into a ring. This made the main body smaller, so it spun even faster, throwing off another ring. It's like peeling an onion layer by layer. The central remnant became the sun, and the rings formed the planets. Laplace's theory also had limitations. First, just like Kant, he didn't explain where his starting material, the rotating nebula, came from. But the fatal flaw was internal. According to his logic, the sun, being the final, most contracted remnant, should be spinning the fastest of anything in the solar system. In reality, the sun rotates quite slowly compared to several planets. This direct contradiction was a massive problem for the nebular hypothesis. Moving away from nebulae entirely, we have the Chamberlain-Moulton planetesimal hypothesis. This theory starts with our sun already existing as a young star. A much more massive star passed very close by. The immense gravitational pull of this visiting star ripped a huge stream of material right out of the sun's body. This ejected material was left orbiting the sun, where it eventually collided and gathered together to form the planets and other bodies. The fourth and most scientifically supported theory is the accretion model by Otto Schmidt and Victor Safronoff. It starts with a cloud of gas and dust. Here, particles underwent inelastic collisions, meaning they didn't shatter, they stuck together. Dust stuck together to form boulders. Boulders collided to form larger bodies called planetesimals, and these accreted to form full-sized planets. As these planets grew massive enough, their own gravity pulled them into the spherical shapes we see today. This brings us to a deeper question. Where did all that gas and dust come from? The dominant answer is the Big Bang hypothesis. It proposes that roughly 13.7 billion years ago, all matter in the universe was packed into a single atom-sized point called a singularity, which had infinite density. Then, for reasons we still don't understand, it exploded. This released all the matter that exists today. Since matter cannot be created or destroyed, everything around us is made of that exact same primordial material. To understand the evidence for the Big Bang, we need to understand electromagnetic radiation. Radiation travels in waves, measured by wavelength, the distance between crests. The spectrum ranges from tiny gamma rays to massive radio waves. Human eyes can only see a tiny sliver, visible light. where violet has the shortest wavelength and red has the longest. Crucially, the hotter an object is, the faster its particles vibrate, emitting shorter, higher energy wavelengths. Because light travels in waves, its appearance changes if the source is moving. If an object is moving toward you, the light waves get compressed, making the wavelength shorter. We call this blue shift. Conversely, if an object is moving away from you, the waves are stretched out, making the wavelength longer. This is called redshift. The object isn't actually changing color, it's a perceptual shift caused by relative motion, similar to the Doppler effect you hear when an ambulance drives past. This brings us to Edwin Hubble's monumental discovery. When Hubble looked at distant galaxies, he found that every single one of them exhibited redshift. Furthermore, the further away a galaxy was, the faster it was receding. This became Hubble's law. The universe is expanding. If everything is moving apart today, then if you rewind the clock billions of years, everything must have started from a single point. This is the primary evidence for the Big Bang. The second major piece of evidence is cosmic microwave background radiation, or CMBR. For the first 300,000 years after the Big Bang, the universe was so dense that no light could escape. When atoms finally formed, the universe's first light was released. Over 13 billion years, as the universe expanded, those initial high-energy waves were stretched out into long microwaves. Today, we detect this faint radiation uniformly in every direction. It is literally a baby photograph of the early universe. When we look at the universe, everything we can see, touch, or interact with makes up just 5% of it. The rest is completely invisible to our instruments. About 27% is dark matter, which acts as the gravitational glue holding galaxies together. It pulls things inward. The remaining 68% is dark energy, a repulsive force that is actively pushing the universe apart and accelerating its expansion. We call them dark simply because they are hidden from us. We only know they exist because of their effects. Following the Big Bang, the universe was filled mostly with hydrogen gas. Because dark matter was unevenly distributed, certain regions had a slightly stronger gravitational pull. Hydrogen gas naturally congregated in these high-gravity pockets. As massive amounts of gas gathered, these regions became the birthplaces of stars, eventually forming the billions of galaxies we see today. Galaxies come in 4 main shapes. Spiral galaxies, like our Milky Way, have a central bulge of old stars and spiral arms where active star formation happens. Lenticular galaxies look similar from the side, but lack spiral arms and have less star formation. Elliptical galaxies are the oldest. They are smooth, oval-shaped, and have exhausted almost all their star-forming gas. Finally, irregular galaxies have no defined shape, but are rich in gas and actively forming new stars. At the center of every galaxy lies a supermassive black hole. Ours is called Sagittarius A star. While black holes themselves emit no light, their immense gravity pulls in surrounding material. As this material swirls inward, violent collisions generate intense heat and light. If a black hole is actively feeding, we call it an active galactic nucleus, and it glows brilliantly. If it's not currently feeding, like ours, it's a passive nucleus, and the center appears relatively dim. Active galactic nuclei are classified by their energy output. Seyfert galaxies are the dimmest of the active bunch, emitting mostly in infrared or X-rays rather than visible light. Quasars are the heavyweights. They continuously release staggering amounts of radiation, making them the brightest objects in the universe. Blazars are a bit different. They are characterized by sudden, highly focused jets of energy blasting outward from the black hole's north and south poles. Let's zoom in on how individual stars are born. Within a galaxy, gravity pulls hydrogen and dust together into a stellar nebula. As it collapses inward, it forms a dense protostar. The pressure at the core becomes so extreme that hydrogen atoms are forced together to create helium. This is nuclear fusion, and it releases massive amounts of energy. Once fusion begins, the star enters its main sequence, the stable, active phase of its life, just like our sun is in right now. Bringing it closer to home, our solar system is entirely dependent on its only star, the sun. Planets don't generate their own energy. They get it all from the sun's nuclear fusion. Our sun is a population 1 star, meaning it contains heavier elements, unlike the theoretical first stars. It's about 4.6 billion years old, composed of 71% hydrogen and 27% helium, and has enough fuel to stay in its main sequence for another 3 to 4 billion years. Not everything orbiting the sun is a planet. To earn that title, an object must meet 4 strict conditions. First, it must have a defined orbit around the sun. Second, it must have enough gravity to pull itself into a nearly spherical shape. Third, it cannot be a moon orbiting another planet. And fourth, it must have cleared its orbital neighborhood, meaning its gravity controls or has expelled any other objects sharing its path. This fourth condition is exactly why Pluto was demoted in 2006. Pluto orbits in a crowded region called the Kuiper Belt, meaning it has not cleared its neighborhood. Objects that meet the first three conditions but fail the fourth are classified as dwarf planets. Currently, we recognize 5 dwarf planets in our solar system: Ceres, Pluto, Eris, Haumea, and Makemake. A satellite, or moon, is a body that directly orbits a planet. Earth has 1, while Saturn has a staggering 274. Mercury and Venus have none. However, there are also quasi-moons. These are actually asteroids orbiting the Sun, but their path makes them look like they are orbiting a planet. They aren't gravitationally bound to the planet, and their apparent relationship is only temporary. Venus has a famous quasi-moon named Zoozve. Asteroids are rocky or metallic objects that orbit the Sun but fail the planetary test because they aren't spherical and often lack stable orbits. The vast majority of them are concentrated in the asteroid belt, located between Mars and Jupiter. They are trapped there primarily by the immense gravitational pull of Jupiter, which prevents them from coalescing into a planet and keeps them corralled in that specific region. Interestingly, some asteroids share a planet's orbit. These are called Trojans. They exist at Lagrangian points, specific spots where the gravitational pull of the Sun and the planet perfectly balance out, creating a stable pocket. L4 and L5 sit 60 degrees ahead and behind the planet. There are also points along the Sun-planet line, like L1. India's Aditya L1 mission is parked exactly at the Earth-Sun L1 point, giving it an uninterrupted view of the Sun. These 3 terms describe the exact same object at different stages. A meteoroid is a rock moving randomly through space. Think D for dancing in space. When it hits Earth's atmosphere, friction heats it up and burns brightly. We call this a meteor, or a shooting star. Most burn up completely, but if a piece is large enough to survive the fall and actually strike the ground, it becomes a meteorite. Comets are essentially dirty snowballs, icy bodies with metallic cores on highly stretched elliptical orbits. When a comet gets close to the Sun, the heat vaporizes its ice, creating a glowing cloud called a coma. The solar wind then blows this gas and dust outward, creating a spectacular tail. Because it's pushed by the solar wind, a comet's tail always points directly away from the Sun, regardless of which way the comet is traveling. Where do comets come from? We measure outer solar system distances in astronomical units, or AU, which is the distance from Earth to the Sun. The Kuiper Belt sits just beyond Neptune, between 30 and 50 AU. It's full of icy bodies and is the source of short-period comets like Halley's. Much further out, starting around 2000 AU, is the Oort cloud. This is a massive, spherical shell surrounding our entire solar system, and it's the birthplace of long-period comets. The Sun continuously blasts out a stream of charged particles called the solar wind. This wind creates a massive bubble called the heliosphere, which encompasses all the planets. As the supersonic wind hits the interstellar medium, it abruptly slows down at the termination shock, moves through a turbulent zone called the heliosheath, and finally stops completely at the heliopause, the true edge of the solar system. And as our whole system orbits the galaxy, it creates a bow shock in front of it, much like a ship moving through water. Our 8 planets are divided into 2 distinct groups. The 4 inner planets, Mercury, Venus, Earth, and Mars, are terrestrial. They are rocky, dense, have no rings, and very few moons. The 4 outer planets are giants. Jupiter and Saturn are gas giants, while Uranus and Neptune are ice giants. Because they formed further away, they are less dense, have extensive ring systems, dozens of moons, and take decades or even centuries to complete a single orbit. Almost all planets rotate from west to east, which is why the Sun appears to rise in the east. But Venus and Uranus are rebels. They rotate backward, from east to west. Planets also have an axial tilt. Earth is tilted at 23.5 degrees, likely due to an ancient collision, which gives us our seasons. Uranus takes this to the extreme. It was knocked completely on its side with a 90-degree tilt, meaning its poles point directly at the Sun during its orbit. Finally, let's look inside the Sun. At the very center is the core, where temperatures hit 15 million degrees and nuclear fusion occurs. The energy produced here moves outward into the radiative zone, where it travels purely as electromagnetic radiation, photons bouncing around for thousands of years. Next is the convective zone, where heat is transferred by convection. Hot plasma rises, cools, and sinks back down in massive loops. This is different from conduction, which is how heat travels through solid objects by atoms vibrating against each other. Before we move on, let's highlight a few critical distinctions for examination purposes. Remember that black holes are dead stars, not dark matter. Pulsars are a type of neutron star, whereas quasars and blazars are active galactic nuclei, not individual stars. Also, the Chandrasekhara limit applies to the remnant core of a star, not its total mass. Finally, when we talk about solar wind being supersonic, that is relative to the speed of sound, not light. Keeping these specifics in mind sets us up perfectly to dive into the detailed planetary analysis in our next segment. Moving right along into our next major concept, let's look at the Goldilocks zone. The name comes directly from the famous children's fairy tale about a girl who breaks into a house belonging to three bears. In the story, she finds that one bowl of porridge is too hot, one is too cold, but the middle one is just right. She applies the same logic to their beds. The moral is that she consistently prefers the middle option, entirely avoiding the extremes. Scientists adopted this exact concept for astronomy. When searching for extraterrestrial life, we look for planets that sit at a comfortable middle distance from their star. If a planet is too close, it's too hot. If it's too far, it's too cold. The zone in the middle is just right for liquid water, and in scientific terms, we call this the habitable zone. Why are scientists so strictly focused on liquid water? It is because life on Earth, which is the only confirmed example of life we have, is fundamentally dependent on it. Water is the ultimate facilitator. It acts as a solvent for biological reactions, a medium to transport nutrients in and waste out, and a vital temperature regulator. Without liquid water, life as we know it simply cannot exist. But water is incredibly fragile. To remain liquid, a planet's surface temperature must sit strictly between 0 degrees and 100 degrees Celsius at standard atmospheric pressure. Too close to the star and it all boils away into vapor. Too far and it freezes into solid ice. Liquid water demands that perfect Goldilocks distance. It is crucial to understand that the Goldilocks zone is not a fixed universal distance. It is entirely star-specific, depending heavily on the mass and energy output of the individual star. Imagine a massive, luminous, hot star. Its enormous energy output warms a massive region of space, pushing its habitable zone much further away. Conversely, a small, dim, cool star will have a habitable zone tucked very close to it. For our own sun, this zone is centered at approximately 150 million kilometers away. Not coincidentally, that is the exact orbital distance of Earth. If we look at a different star, like Proxima Centauri, our closest stellar neighbor, its Goldilocks zone is sized and positioned completely differently than ours. Because of this reliance on water, our strategy for finding extraterrestrial life is clear. We must look for planets orbiting within their star's habitable zone. Now, the scientific community does acknowledge that life could theoretically exist without water. Science fiction, like the film Project Hail Mary, brilliantly imagines life forms based on entirely different, non-water biochemistries, adapted to radical environments. However, when we are spending billions of dollars to search the cosmos, logic dictates we search for what we know works, Earth-like life based on water and carbon chemistry. This concept is so fundamental to modern astronomy that it frequently appears in major examinations, including the UPSC exams. Let us shift our focus to the formation of our own planet. Earth is incredibly old, clocking in at approximately 4.54 billion years. The Sun is just slightly older, at about 4.6 billion years. After the Sun ignited, a massive cloud of leftover gas and dust, known as the solar nebula, continued to swirl around it. Earth formed from this debris through a process called gravitational accretion. Essentially, solid particles and gases began to clump together due to gravity. As these clumps grew, their gravitational pull increased, attracting even more material, building up into a progressively larger planetary body over millions of years. When Earth first formed, it was just a chaotic, undifferentiated ball of mixed materials. But early Earth was extremely hot and largely molten. During this molten phase, a process called density differentiation occurred. Think of what happens when you mix oil and water. The denser water sinks and the lighter oil floats. The exact same physics applied to the molten Earth. The heaviest, densest materials, primarily iron and nickel, sank straight to the center to form the core. The lighter materials, like silicate rocks, migrated outward to form the mantle and the crust.
This is why our planet has a layered internal structure, with a dense center and a light surface, spanning a radius of about 6,400 kilometers. This iron core is also what generates our protective magnetic field. After density differentiation established Earth's internal layers, the outermost layer, the crust, began to cool down. As rock cools, it physically contracts. This massive planet-wide cooling and contraction caused the early crust to buckle, forming massive cracks and deep depressions, or basins. This created the very first varied topography on Earth. Furthermore, those deep cracks provided a direct pathway for the intensely hot, pressurized material from the mantle to reach the surface, kicking off a period of violent, widespread volcanic activity across the young planet. As the Earth was differentiating, the absolute lightest elements trapped inside, specifically hydrogen and helium, seeped out to the surface through a process called degassing. This formed Earth's very first atmosphere. However, this stage 1 atmosphere did not last long. Hydrogen and helium are incredibly light. At the same time, the young sun was blasting the solar system with intense solar wind, a stream of highly energetic particles. Because Earth's magnetic field hadn't fully formed yet to deflect this energy, the solar wind literally blew the atmosphere away. It is like placing a rock and a piece of cotton on the ground on a windy day. The heavy rock stays, but the light cotton is effortlessly blown away.
With the first atmosphere gone, a second one began to form, driven entirely by the intense volcanic activity we mentioned earlier. As volcanoes erupted through the cracked crust, they didn't just release lava, they released colossal volumes of trapped gases from the Earth's interior. This process is known as volcanic outgassing. The gases pumping into the sky included massive amounts of water vapor, carbon dioxide, ammonia, nitrogen oxides, sulfur dioxide, and argon. This stage 2 atmosphere was incredibly dense and toxic by today's standards, and most notably, it contained almost zero free oxygen. It was an atmosphere dominated by carbon dioxide and water vapor. Then, something miraculous happened that completely changed the planet. Life appeared. We believe the first organisms arose between 3.8 and 4.2 billion years ago. These early life forms survived by consuming the carbon and nitrogen compounds available in that harsh stage 2 environment. But eventually, some organisms evolved a game-changing ability, photosynthesis. They learned to use sunlight to convert the abundant carbon dioxide and water into food, releasing oxygen as a byproduct. Over hundreds of millions of years, these organisms multiplied, pumping massive amounts of oxygen into the air, while other bacteria processed nitrogen compounds into nitrogen gas. Life didn't just survive in Earth's atmosphere. Life actively engineered it into the 78% nitrogen and 21% oxygen mix we breathe today. But what happened to all that water vapor pumped out by the early volcanoes? As the Earth's surface slowly cooled down from its molten state, the atmosphere cooled with it. Eventually, the temperature dropped enough for that massive volume of water vapor to condense into clouds. And then it started to rain. This wasn't a normal storm. This was a relentless planet-wide deluge that lasted for millions upon millions of years. All that rainwater flowed downhill, eventually pooling in those massive basins and depressions that had formed when the crust originally cracked and contracted. That combination of volcanic vapor, planetary cooling, and crustal basins gave birth to Earth's oceans. With oceans in place, the stage was set for life. As we noted, life began roughly 3.8 to 4.2 billion years ago. But one of the most profound discoveries in biology is that every single living thing on this planet, from the bacteria in the soil, to the trees outside, to your pets, to you and me, shares a single common ancestry. Scientists refer to this hypothetical original organism as LUCA, the last universal common ancestor. It is a staggering realization that the entire diversity of the biosphere traces its lineage back to one single microscopic starting point in the ancient oceans.
How did LUCA come to be? While some scientists suggest life's ingredients arrived via asteroids, a concept called panspermia, others wanted to see if life could arise spontaneously from Earth's own chemistry. Enter the famous Miller-Urey experiment. Stanley Miller and Harold Urey built a closed glass system and filled it with the exact chemicals present on early Earth: water, methane, ammonia, and hydrogen. They then added heat and simulated lightning to replicate early Earth's energy. Astoundingly, after running the experiment, they found that amino acids, the essential building blocks of proteins, had formed spontaneously in the flask. They didn't create a living cell, but they proved that the chemical leap from non-living gases to the building blocks of life is entirely plausible.
Now let's look at some fundamental mechanical facts about our planet, starting with its posture. Earth does not spin perfectly upright relative to its orbit around the sun. It is tilted on its rotational axis at an angle of 23.5 degrees from the vertical. Astronomers believe this severe tilt is the scar of a catastrophic collision with a massive asteroid or planetoid during the chaotic early days of the solar system. The impact literally knocked Earth off its vertical axis, and it has maintained this 23.5-degree lean ever since. This specific tilt is incredibly important because it is the sole reason we experience seasons as we orbit the sun. Fascinatingly, that 23.5-degree tilt is currently being altered by human activity. It comes down to the physics of mass distribution. When you move massive amounts of weight around a spinning object, its axis of rotation shifts. Humans are currently doing this in two major ways. First, through the massive extraction of groundwater from deep underground aquifers, particularly in regions like India and North America, pumping it to the surface where it flows into the oceans. Second, climate change is melting massive polar glaciers, moving billions of tons of water from the poles toward the equator. This human-driven redistribution of mass is actually causing a measurable wobble and shift in Earth's rotational axis, a fact so significant it was featured in the 2025 UPSC prelims. Let's talk about how we measure a day. You probably think a day is exactly 24 hours, but physically it takes Earth exactly 23 hours, 56 minutes, and 4 seconds to complete one full 360-degree rotation on its axis. We call this true physical rotation a sidereal day, measured relative to the distant stars. So why is our clock day 24 hours? Because while Earth is spinning, it is also moving forward along its orbit around the sun. By the time it completes one 360-degree spin, it has moved a bit along its orbital path, meaning the sun is no longer in the exact same spot in the sky. Earth has to spin for about 4 extra minutes to catch up and face the sun directly again. That brings the solar day to an even 24 hours.
We face a similar mathematical headache with the year. A sidereal year, which is the exact time it takes Earth to complete one full physical orbit around the sun, is 365 days, 5 hours, and 48 minutes, essentially 365 1/4 days. However, our standard Gregorian calendar year is defined as exactly 365 days. This leaves a discrepancy of nearly 6 hours every single year. If we ignored this, our calendar would slowly drift completely out of sync with the seasons. To fix this, we let those extra hours accumulate for 4 years, which adds up to almost exactly 24 hours, and we add that as one extra day, February 29th, to our calendar. This is why we have leap years.
Earth's rotation isn't just tricky to measure, it's actually slowing down over geological time. During the age of the dinosaurs, a day was only about 21 to 23 hours long. 3 main factors are hitting the brakes on our planet. First, surface friction. Earth spins west to east, but major trade winds and ocean currents flow east to west, creating massive drag. Second, internal friction. The molten iron in Earth's outer core sloshes around and rotates at a slightly different speed than the solid crust, creating internal drag. Finally, and most significantly, the moon is stealing our rotational energy. The moon's gravity pulls on our oceans, creating tides. This tidal friction acts like a brake pad on the rotating Earth, transferring our rotational energy to the moon, which causes the moon to slowly spiral further away from us. Before we move on to orbits, let's quickly clarify the direction of Earth's spin. If you were to fly in a spaceship directly above the geographic North Pole and look straight down at the planet, you would see the Earth rotating in a counterclockwise or anti-clockwise direction. This is a standard foundational fact in geography and astronomy, and keeping this counterclockwise motion in mind is incredibly helpful when you are trying to interpret complex maps or diagrams of atmospheric and oceanic circulation. Now let's look at Earth's path around the sun. Earth's orbit is not a perfect circle. It is an ellipse, which is essentially a stretched-out circle. In a perfect circle, the center is equidistant from all edges, but an ellipse has 2 focal points instead of one center. The sun does not sit in the exact geometric center of our orbit, it sits off to the side at one of these focal points. Because of this off-center geometry, the physical distance between the Earth and the sun is not constant. It constantly varies as Earth travels along its elliptical path throughout the year. Because the distance varies, there is a specific point in the year when Earth is closest to the sun. This point is called perihelion. A great way to remember this is using the letter P. P for perihelion, P for passing close by, or P for periphery. Perihelion occurs every year around January 3rd. Now, this often confuses people. Earth is physically closest to the massive heat of the sun in early January, which is the dead of winter in the northern hemisphere. This perfectly proves our earlier point. Seasons are not caused by how close we are to the sun. They're dictated entirely by the 23.5-degree axial tilt. On the opposite side of the orbit is aphelion, the point where Earth is farthest away from the sun. The mnemonic here is easy. A for aphelion, A for away. Aphelion occurs around July 4th. Again, note the counterintuitive timing. We are furthest from the sun's heat during the peak of the northern hemisphere's summer. It's worth noting that the actual difference in distance between perihelion and aphelion is only about 3%. It's a massive distance in kilometers, but percentage-wise, it's too small to override the powerful seasonal effects caused by Earth's axial tilt. That 23.5-degree axial tilt doesn't just cause seasons, it also causes the length of our days to change throughout the year. Because the Earth remains tilted in the exact same direction as it orbits the sun, the angle at which sunlight strikes different latitudes constantly shifts. Sometimes the northern half leans into the light, sometimes it leans away. This shifting exposure changes how many hours of daylight a specific location receives. There is only one exception, the equator. Because the equator lies exactly halfway between the poles, it is always equally illuminated and shadowed as the planet spins, guaranteeing exactly 12 hours of day and 12 hours of night, 365 days a year. Let's track this cycle, starting with the June solstice, which occurs around June 21st or 22nd. At this point in the orbit, the northern hemisphere is tilted at its absolute maximum toward the sun. Because it's leaning into the light, the northern hemisphere experiences its longest day and shortest night of the year. The sun's most direct, intense rays fall exactly on the Tropic of Cancer at 23.5 degrees north latitude. If you travel far enough north, past the Arctic Circle at 66.5 degrees north, the tilt is so extreme that the sun never sets at all, creating a 24-hour period of daylight known as the midnight sun. 6 months later, Earth reaches the opposite side of its orbit for the December solstice, around December 21st to 23rd. Earth's tilt hasn't changed direction, but its position relative to the sun has. Now, the southern hemisphere is tilted maximally toward the sun. The situation flips entirely. The southern hemisphere gets its longest days and shortest nights, and the direct rays of the sun fall on the Tropic of Capricorn at 23.5 degrees south. Down at the Antarctic Circle, they experience the 24-hour midnight sun, while the Arctic Circle is plunged into 24 hours of total darkness. Halfway between the solstices, we have the equinoxes. The word equinox comes from Latin meaning equal night. During an equinox, Earth is at a point in its orbit where its tilt is completely neutral relative to the sun. It is leaning neither toward nor away from it. As a result, the sun's direct rays fall perfectly on the equator, and every single latitude on Earth experiences exactly 12 hours of daylight and 12 hours of darkness. This happens twice a year, the March equinox around March 20th and the September equinox around September 22nd. We use these neutral terms now, rather than spring or autumn, because the seasons are opposite in the northern and southern hemispheres. To visualize this cycle, let's look at India, located in the northern hemisphere. In late December, during the solstice, India experiences its shortest, darkest days of winter. As the Earth moves toward March, the days gradually lengthen until the March equinox, where day and night balance at exactly 12 hours each. Moving into June, the days keep getting longer, culminating in the June solstice, the longest day of the summer. After June, the days begin to shorten again, balancing out at 12 hours during the September equinox and continuing to shorten until we are back in the dark days of December, completing the annual cycle. This dynamic relationship between Earth and the sun sets the stage perfectly for our next topic, where we will examine Earth's closest neighbor, the Moon. Let's examine the Moon, Earth's only natural satellite. A natural satellite is a celestial body orbiting a planet, unlike human-made artificial satellites. Our Moon is roughly 1/4 the size of Earth, or about 27% of its diameter. Looking at the inner solar system, Earth is the first planet to have a moon. Mercury and Venus have none, while Mars has 2 small ones, Phobos and Deimos. As we move to the outer gas giants, the numbers explode. Jupiter has many, and Saturn currently boasts over 274 confirmed moons. The Moon's orbit around Earth is not a perfect circle. It is an ellipse with Earth at one focal point. This means the distance between the Earth and the Moon changes constantly. The point where the Moon is closest to Earth is called perigee. You can remember this with the letter P for pass or periphery. The farthest point is called apogee, A for away. When a full moon happens to occur exactly at perigee, it appears unusually large and bright in our sky, a phenomenon popularly known as a supermoon. Have you ever noticed that the man in the moon pattern never changes? Earth always sees the exact same face of the moon, regardless of its phase. The so-called far side remained completely hidden from human eyes until spacecraft finally orbited it. This happens because of a phenomenon called tidal locking. Tidal locking occurs when a body's rotation period, the time it takes to spin once on its axis, is exactly equal to its revolution period, the time it takes to orbit its partner. For the moon, both take about 27.3 days. To understand this, imagine putting your fist on a table to represent Earth. If you walk in a circle around your fist, always keeping your face pointed toward it, you will have spun around exactly once by the time you complete the circle. The moon does rotate, but because its rotation matches its orbit, we only see its front. In the distant past, the young moon actually spun much faster, showing all its sides. Over billions of years, Earth's gravitational pull exerted a drag or torque on the moon. This tidal friction slowed the moon's spin until it perfectly matched its orbit. Shifting our focus back to Earth, let's summarize the critical functions of geomagnetism, or Earth's magnetic field. First, it acts as a planetary shield, deflecting and trapping deadly charged particles from solar storms and coronal mass ejections. Second, it prevents atmospheric stripping. By redirecting the solar wind, it keeps our atmosphere intact, a protection Mars lost when its magnetic field died, leading to the loss of its thick early atmosphere. Finally, it provides a framework for navigation, utilized by centuries of human compasses, modern GPS systems, and the biological instincts of many animals. Let's quickly review some essential terminology, starting with the sun. The core is the innermost layer where nuclear fusion occurs at millions of degrees. Energy moves outward through the radiative zone via radiation, then through the convective zone, where hot plasma rises and cool plasma sinks. The photosphere is the visible surface we see, which emits sunlight. Above that is the chromosphere, and finally the corona, the outermost atmospheric layer. Surprisingly, the corona is the hottest layer, reaching millions of degrees, and is the source of the solar wind. Continuing with solar activity, the sun is made of plasma, a superheated state of matter full of charged ions and electrons. The sun constantly emits a solar wind of these particles. Occasionally, it releases a massive burst of plasma called a coronal mass ejection, or CME. A solar flare, by contrast, is a sudden flash of pure energy caused by snapping magnetic field lines. You'll also see sunspots, which are darker, cooler patches on the photosphere. These fluctuate over an 11-year solar cycle, peaking at solar maxima with high insolation and dropping at solar minima. Now for Earth's orbital terms. Perihelion is when Earth is closest to the Sun, around January 3rd, while aphelion is when we are furthest, around July 4th. A sidereal day is Earth's true rotation time relative to the distant stars, taking exactly 23 hours, 56 minutes, and 4 seconds, which is slightly shorter than our conventional 24-hour calendar day. A sidereal year is the exact time to orbit the Sun. We also have solstices in June and December, marking our longest and shortest days, and equinoxes in March and September, when day and night are perfectly equal globally. Rounding out our terminology, the Goldilocks zone is the habitable region around a star where liquid water can exist. LUCA stands for the last universal common ancestor of all life. Density differentiation is how early Earth's heavy metals sank to form the core, while lighter rocks formed the crust. The famous Miller-Urey experiment proved that organic building blocks of life could form spontaneously in early Earth conditions. Degassing refers to volcanoes releasing trapped gases to form our secondary atmosphere. Finally, Faraday's law explains that moving electrical charges generate magnetic fields. Moving into our class review, let's revisit the concept of a brown dwarf, often called a failed star. Stars form when clouds of gas and dust collapse under gravity to create a protostar. Normally, the core pressure and temperature build up until nuclear fusion ignites, converting hydrogen to helium and releasing massive energy. In a brown dwarf, the protostar forms, but it simply never gets hot or dense enough to trigger that sustained nuclear fusion. It exists in space, but it fails to ever truly turn on. Let's explore why the moon changes shape in our sky. The fundamental fact to remember is that the moon is a non-luminous body. Unlike the sun, it does not have a nuclear furnace. It generates absolutely no light of its own. We can only see the moon because it acts like a giant mirror, reflecting sunlight. The phases of the moon, the changing shapes we see, are simply the result of our viewing angle. As the moon orbits us, we see different amounts of its sunlit half. When the Earth is directly between the sun and the moon, the entire sunlit side of the moon faces us, creating a full moon, or Purnima. Conversely, when the moon moves between the Earth and the sunlit side faces completely away from us. The side facing Earth is in total shadow, making the moon invisible to us. This is the new moon, or Amavasya. In the intermediate positions along its orbit, we see varying fractions of the lit side, creating the familiar half-moon and crescent shapes. A common question is why we don't usually see the moon during the day. The moon doesn't vanish, it is often physically present in the daytime sky. However, the sun is incredibly luminous. The intense brightness of the sun scatters through our atmosphere, creating a brilliant blue sky that simply drowns out the faint reflected light of the moon. It's like trying to see a flashlight beam outdoors on a sunny day. The light is there, but your eyes can't perceive it against the overwhelming background glare. How did the moon form? We'll look at 3 theories. The first is the fission theory, proposed by George Darwin, the son of Charles Darwin. He suggested that when the Earth was newly formed, it was spinning at an incredibly rapid rate. This extreme rotation generated massive centrifugal forces, which literally flung a huge chunk of material off the Earth and out into space. According to this theory, that ejected fragment eventually stabilized and clumped together to become our moon. The second, and currently most accepted explanation, is the giant impact hypothesis, also known as the Big Splash theory. Billions of years ago, a Mars-sized dwarf planet named Theia collided violently with the early Earth. Just like dropping a massive boulder into a pool of water causes a huge splash, this collision blasted a colossal amount of Earth's crust out into space. This debris formed a ring around the Earth, much like Saturn's rings. Over time, gravity swept all that ring material together into a single sphere, forming the moon. The third and newest idea is the binary exchange capture theory, proposed in 2024. This theory suggests the moon didn't form from Earth at all. Instead, it was originally part of a binary system, 2 celestial bodies orbiting a shared center of gravity out in deep space. When this pair wandered too close to Earth, our planet's strong gravitational pull disrupted them. Earth captured one of the bodies, locking it into orbit as our moon, while the other companion was slingshotted away into space. Let's move on to eclipses. An eclipse simply occurs when one celestial body hides another. In a solar eclipse, or Suryagrahan, the moon passes directly between the Earth and the sun. The moon blocks the sunlight, casting a shadow on Earth and hiding the sun from our view. In a lunar eclipse, or Chandragrahan, the Earth passes between the sun and the moon. The Earth blocks the sunlight, and its massive shadow falls across the moon, causing the moon to darken. You might wonder, how can the tiny moon completely cover the gigantic sun? It's all about perspective. If you hold your hand right up to your face, it can completely block your view of a large building in the distance. The sun is massive, but it is 150 million kilometers away. The moon is tiny, but it is only 380,000 kilometers away. Because the moon is so much closer to us, it appears in our sky to be the exact same size as the distant sun, allowing it to perfectly cover the solar disk. Since a new moon puts the moon between Earth and the sun, why don't we have a solar eclipse every month? The answer lies in orbital tilt. The Earth's orbit around the sun and the moon's orbit around the Earth are not perfectly flat with each other. They are tilted at an angle. During most new and full moons, the moon is physically too high or too low to cast a shadow on Earth, or for Earth to cast a shadow on it. Eclipses only happen when the moon crosses the exact intersection points of these 2 tilted planes. To understand the types of eclipses, we need to understand shadows. Imagine standing in a room with 2 light bulbs. If you block both bulbs completely, you cast a pitch-black shadow called the umbra, but around that dark center, there is a softer shadow where you are only blocking one of the bulbs, allowing some light to bleed in. This lighter, partial shadow is called the penumbra. Celestial bodies cast these exact same umbra and penumbra shadows out into space. When the moon's shadow sweeps across the Earth, it brings both shadow zones. If you're standing in the direct path of the moon's umbra, the darkest part of the shadow, you will experience a total solar eclipse. The sun will be completely blocked, and the sky will turn dark in the middle of the day. If you're standing slightly outside that path, in the penumbra, you will only see a partial solar eclipse, where the moon appears to take a bite out of the sun, but daylight remains. Just seconds before the moon completely covers the sun, a breathtaking optical illusion occurs, the diamond ring effect. As the moon's rugged edge covers the last sliver of the sun, a single brilliant point of sunlight shines through a deep valley on the moon. At the same time, the sun's faint outer atmosphere, the corona, becomes visible as a glowing halo. Together, they look exactly like a giant diamond ring in the sky. Right before this, you might see Bailey's beads, multiple little diamonds caused by sunlight streaming through several lunar valleys at once. Lunar eclipses follow the exact same shadow rules. A total lunar eclipse happens when the entire moon plunges into the Earth's umbra. In this deep shadow, no direct sunlight can reach the lunar surface. A partial lunar eclipse occurs if the moon only grazes the umbra, or if it only passes through the lighter penumbra. In a partial eclipse, the moon just looks a bit dimmer, or has a dark curved bite taken out of its edge. During a total lunar eclipse, the moon doesn't just go black, it turns a haunting deep red, known as a blood moon. Why? Because of Earth's atmosphere. Sunlight contains all colors. As sunlight grazes the edges of the Earth, our atmosphere scatters away the shorter blue wavelengths, which is why our daytime sky is blue. But the longer red wavelengths push straight through the atmosphere, bend around the curve of the Earth, and project onto the dark moon. The moon reflects this filtered red light back to us.
You've likely heard the phrase, once in a blue moon. A blue moon has absolutely nothing to do with the moon turning blue. It is purely a quirk of our calendar. The lunar cycle takes about 29.5 days, which is slightly shorter than most of our calendar months. Because of this mismatch, occasionally a single calendar month will squeeze in 2 full moons. When that happens, the second full moon in that month is culturally referred to as a blue moon.
Let's shift to Earth's geography, starting with latitudes. Latitudes are imaginary lines running east to west across the globe, used to pinpoint locations. Because they never intersect, they are also called parallels. They shrink in circumference as you move from the center to the poles. The granddaddy of them all is the equator, at 0 degrees. It splits the Earth into the northern and southern hemispheres, and is unique because it experiences exactly 12 hours of daylight and 12 hours of darkness every single day of the year.
Moving away from the equator, we hit the tropics. The Tropic of Cancer, at 23.5 degrees north, is the highest latitude where the sun can be directly overhead, which happens on the June solstice. The Tropic of Capricorn, at 23.5 degrees south, is the southern equivalent, peaking on the December solstice. The band between these two lines is the tropical zone, receiving the most intense solar heat. Halfway between the solstices are the equinoxes, in March and September, where the sun is directly over the equator, giving the whole planet equal day and night.
Near the poles, we find the Arctic and Antarctic circles at 66.5 degrees north and south. These lines mark the boundaries of extreme daylight. Above the Arctic Circle, during the June solstice, the sun never sets, creating the famous midnight sun, a full 24 hours of daylight. 6 months later, during the December solstice, the sun never rises, resulting in 24 hours of darkness. The Antarctic Circle experiences the exact same phenomena, but perfectly reversed on the calendar. Now for longitudes. These are imaginary vertical lines running from the North Pole to the South Pole. Unlike latitudes, longitudes are not parallel. They converge at the poles like the slices of an orange. The starting point, 0 degrees longitude, is called the prime meridian. Why there? Because during the era of global mapmaking, the British Empire was the dominant naval power, so they drew the zero line right through the Royal Observatory in Greenwich, London. This established Greenwich Mean Time, or GMT, as the baseline for the word's clocks. Longitudes are the secret to how we calculate time zones. The Earth rotates 360 degrees every 24 hours. If you do the math, that's 15 degrees of longitude per hour, or 1 degree every 4 minutes. Because the Earth rotates west to east, locations to the east see the sunrise first, meaning their clocks are ahead. For example, India's standard meridian is 82.5 degrees east. Multiply 82.5 by 4 minutes, and you get 330 minutes, or 5.5 hours. Therefore, Indian Standard Time is exactly 5 hours and 30 minutes ahead of GMT. If you keep moving east, adding time, you eventually run into a paradox where you meet the people who moved west and subtracted time. To fix this on our spherical globe, we have the International Dateline, located roughly at 180 degrees longitude, exactly opposite the prime meridian. This is where the calendar date officially flips.
If you cross it traveling east toward America, you subtract a day from the calendar, effectively getting to live that day twice. If you cross it traveling west toward Asia, you jump forward a day, losing a day entirely. The international dateline is not a perfectly straight line. If it were, it would slice right through certain countries, meaning you could walk across the street and be in tomorrow. To prevent administrative chaos, the line zigzags to detour around eastern Russia, the U.S. Aleutian Islands, and the Pacific nation of Kiribati. Speaking of administration, while India uses one time zone, massive countries like the U.S. and Russia use multiple zones, 5 and 11 respectively. France actually holds the record with 12, thanks to its many overseas territories.
Antarctica presents a fascinating time zone puzzle. Because all lines of longitude converge at the South Pole, you could technically walk through all 24 time zones in a few seconds. So what time is it there? Practically, each scientific research station just uses the time zone of its home country. The Indian stations, Bharati and Maitri, run on Indian Standard Time, while American stations run on U.S. time. When scientists from different countries need to schedule a meeting, they simply convert their local times to GMT to coordinate.
Let's review some key phenomena from past questions, starting with black holes. A black hole is a region of space where gravity is so intense that nothing, not even light, can escape. The boundary where this occurs is called the event horizon, the ultimate point of no return. At the very center lies the singularity, a point of infinite density. Stellar black holes are formed when massive stars run out of nuclear fuel and collapse inward under their own immense gravity. Related to black holes are quasars, which stands for quasi-stellar radio sources. These are the most luminous and powerful objects in the known universe. A quasar is actually an active galactic nucleus powered by a supermassive black hole. As the black hole aggressively consumes surrounding gas and dust, that matter forms an accretion disk. The friction heats the disk to millions of degrees, emitting so much energy that a single quasar can outshine an entire galaxy of 100 billion stars. Here's a classic geography question. Why does Bombay, or Mumbai, have longer sunshine after 5 p.m. office hours than Calcutta? It comes down to longitude. Calcutta is much further east at 88 degrees, while Mumbai is at 72 degrees. Because the Earth rotates west to east, the sun physically sets earlier in the east. However, both cities share the exact same clock time, Indian Standard Time. Therefore, when the clock strikes 5 p.m., the sun is already setting in Calcutta, but Mumbai still has over an hour of daylight left. Another great question. Since half of India lies north of the Tropic of Cancer, why is it classified as a tropical country? First, the entire country's climate is dominated by the tropical southwest monsoon. Second, even the northern plains experience scorching tropical-level summer temperatures. Most importantly, the massive Himalayan mountain range acts as a wall, blocking freezing continental air from Central Asia. Without that cold air, northern India lacks a true, prolonged temperate winter, allowing tropical flora and fauna to thrive nationwide. Looking at space debris, what is the difference between a comet and a meteor? A comet is essentially an icy, dirty snowball originating from the deep outer solar system. When it gets close to the sun, the ice vaporizes, creating a massive glowing tail. A meteor, on the other hand, is a small piece of rocky or metallic debris that enters Earth's atmosphere. The intense friction causes it to burn up, creating a brief streak of light we call a shooting star. If it hits the ground, it's called a meteorite. Speaking of comets, Comet Shoemaker-Levy 9 made history in 1994. This comet wandered too close to Jupiter and was torn into 21 fragments by the planet's immense gravity. Astronomers watched in awe as these fragments slammed into Jupiter's atmosphere, creating fireballs larger than Earth. This was the first time humans directly observed a collision between two solar system bodies. It perfectly demonstrated how Jupiter acts as a cosmic vacuum cleaner, absorbing dangerous impacts and protecting inner planets like Earth. It's easy to think of the sun as sitting still while planets orbit it, but the entire solar system is actually in constant motion. The sun, carrying all its planets, orbits the supermassive black hole at the center of the Milky Way galaxy. We are hurtling through space at about 220 kilometers per second. Even at that incredible speed, it takes us up to 250 million years to complete one single galactic orbit, known as a cosmic year. As we orbit, we also bob up and down through the galactic plane. In our search for extraterrestrial life, Saturn's largest moon, Titan, is a massive target. Titan is incredibly unique because it is the only moon in the solar system with a thick, dense atmosphere, even thicker than Earth's.
While its surface is freezing cold at -179 degrees Celsius, it has an active weather system. It actually rains on Titan, filling flowing rivers and vast lakes, but these bodies of liquid are made of methane and ethane, not water. Beyond our solar system, scientists look for exoplanets. In 2010, the announcement of a planet named Gliese 581g made global headlines. Located 20 light-years away, it was celebrated as the first exoplanet found squarely in its star's Goldilocks zone, the perfect distance where temperatures allow liquid water to exist. Although later data has cast serious doubt on whether Gliese 581g actually exists, the discovery process proved that red dwarf stars could potentially host habitable Earth-like worlds.
To wrap up our journey through the cosmos and our planet's geography, remember these key points. Our moon is tidally locked to Earth and was likely born from a cataclysmic planetary collision. Eclipses are rare because they require the perfect alignment of tilted orbital planes. On Earth, latitudes dictate our climate zones and seasons, while longitudes are the mathematical basis for our global time zones. Finally, we owe our existence to cosmic shields, from Earth's magnetic field deflecting solar radiation to Jupiter's gravity sweeping up dangerous comets.